use this worksheet as a guide, and it also serves as a summary of this webinar. And anybody who wants a copy of this can contact me. My email, here's my email address, rlopez@maplesoft.com. Okay, contact me, ask for the worksheet, and I'll attach it and send it back. All right, so that's the import of this introduction. Components live in this palette. If you need instruction about how to access palettes, it's at the bottom here. Okay? There is an explanation down here, and it points out that you use the View menu and you select Palettes. And if you pick Arrange Palettes, this dialog will appear, and this explanation tells you what to do with the dialog in order to make sure that you can access the appropriate set of palettes, including the Components palette. Okay, so this is a screenshot of the Components palette. Here's a list of the 5 that I'm going to look at and talk about today. The button, that's this one here. This is a plot window. It looks like a bird flying, but if you look at it, if you could zoom in on it, you'd see it's a graph of a surface. This is a math container. This is the slider, and this is the label. I'm going to talk about those 5. And begin with an example right away. And the example is going to be, insert a button, insert a plot component, tell the button to draw a graph in the plot component. All right, so this is the back of the book answer. This is what we're going to end up with. You have a button, you click the button, and its action is to draw a graph. Okay? All right, so how do we accomplish this? So first of all, we have to insert the button in the plot command. All right, so I've got it inserted over here, and I'm going to go to a blank page, and I'm going to insert a button, and then I'm going to insert a plot window. All right, that's the action that you would have to do to imitate what I've just done. Okay. This says button. Up here it says draw. If you want to say draw, plot, or graph, you got to know how to change the type on that button. And so this tells you how to do it. All right, and what it means, what this is telling you to do is right click. I have a 2-button mouse because I'm in Windows, but if you have a 1-button mouse, there's an equivalent in Linux and Mac. Alt click, Apple click. You would know how to get to the secondary pointer. All right, component properties. Here you see caption, and you change button to whatever you like, graph. And you say OK, and it now says graph. All right, so that's changing the button caption. Let's close that. Now we have to code the button. All right, how do you code the button? Well, where did that go? Here it is. Right click, this time pick Edit, click Action, and you get a dialog like this that comes up. These sharps indicate comment character, comment lines. I get rid of them. And in a moment, I'll tell you what I just threw away. All right, so that's where you put the code for the button. After you put the code for the button, you save the code. You could execute the code with that exclamation point, but you save the code. Okay, so yeah, save the code. Okay, so this is what it looks like. A little screenshot. Get rid of this stuff. What is the content of the comments in this section? three facts. To read what's in a component, you can use this do command. You address the component with a % in front of its name. Now, what is the name of the component? For example, this plot window, I right click and I go to component properties and it says this is plot 12. In other words, I've put in enough plot windows in and out that Maple has given this the name plot 12. Now you can change that name if you like. At the moment, that's how you find out the name of a component. To write to a component, to send information to a component, you can use the do command and you address the component as if it were a variable, or a % component name, equal whatever it is that you want to write to that component. And if you want to read from the component and then assign that information to a variable, you can do it again with the do command. Do variable name equals whatever was in that component. So for this application, this command would be appropriate. Do, now it says plot 0. Oh, for you, or in this new worksheet, that would be plot 0, because it's the first one. Okay, so you may have to change the number according to whatever the plot component name is. Equals plot sin x from 0 to 2 pi. That command will cause the button to draw sin x in the plot window. And that's how this was done. If we go here, you'll see it says plot, do % plot, it's addressing, it's 11, plot sin x, x from 0 to 2 pi. Okay, now a more complicated example. We're going to put in a math container, a button, plot component, and a button. The first button will read from the math container and draw a graph of what it read into the plot component, and the second button will erase the plot. Okay, how do we do that? All right, so this window needs to be stretched. Okay, math container, button, plot window, button. You know how to make the button say draw and erase. And you know how to, you click on the, I showed you over here, how do you build it up over here. So how do we program these buttons? Here are the codes. Behind this draw button, it says to read the contents. Read the content. And assign what is there to the name Q. And then send over to the plot window, whatever the appropriate number is of the plot window, the graph of Q from 0 to 2 pi. Then on this erase button, I have added something in this header line. Now this header line and this terminal line is in the dialog box. It's permanently in the dialog box. Comma plots. And this is the use command that says if there is a command, for example, display, for example, text plot, that is in a package, and you have to look inside a package for that command, this use command tells Maple where to look. Do is in the document tools package, display and text plot are in the plots package, so you would add this comma plots after document tools. Okay, so then how does the erase take place? The erase takes place by writing a blank graph to the plot window. And how do I create a blank graph? Well, it's a graph of a single character, a blank. So text plot puts onto a graph characters. And I'm putting the blank character, space, onto a graph, and I'm putting that graph into this window. And at the same time, if I'm erasing, I send over to the math container null, which erases what's in the math container. All right, so I'm going to begin by clicking on this draw button. So I've built this little tool, and I'm so anxious to test it out. I click on the draw button, and what happens is I get an error. And the content of this error message is essentially this. The box is empty. I have assigned to the variable q nothing. And then I try to plot that, and Maple gets upset. I can't plot nothing. So you can live with that error message, or you can try to cure it. So let's just test this out. Let's put in sine x. Now it's not empty anymore. Click the draw button. I got my graph. Let's see what happens if I do an erase. All right? It behaves the way I intended it to. But there is a problem lurking behind all of this. I call it the globality problem. It is the fact that that variable q that I assign to is global. Here I am outside the component. And if I type q, it will return sine x. So that has q is a global variable. So you can easily break your component structure by typing something at top level outside the component. So you have to think about this. Here was the cure that I was taught, is to wrap everything in a module structure. So a module structure is like a giant procedure, but it's bigger than a procedure. It's a container in which you can put all kinds of stuff. And the important thing is that it supports something local to the module. So what's local to the module is a local variable, and it's not a global variable. So you have module, define q to be local. Now when you read q and draw the graph, q will not break your coding. Now let's take care of the empty container issue. Let's think about that defensive programming aspect. Let's see if we can catch the fact that the container is empty. Here's one way. You have read in q. These square brackets make it a list. This command, number of operands, is counting the number of elements in this list. Now, if the math container was empty, q is null. And the number of operands in this list would be 0. So it says if that's 0, then simply return. Do nothing. Don't issue any errors. Just simply get out of there. So your code would look like this. Module local, read the math container, do a test. If the number of operands is 0, get out of there. And if not, if this is something other than 0, then you can go ahead and draw the graph. Now, if you're an experienced coder, you'll be immediately thinking, but what happens if this is more than one object, or it's a crazy object? You don't get 0, but it could be something you can't graph. You'd still get an error message. Well, let's think about what's happening here. Let's see if we can give the user some feedback if they've left the math container empty. So you read the math container, assign it to Q, and you test. If this is 0, if it's empty, then we're going to display the following message. Enter an expression. And it's going to be placed in the plot window. And it's going to be placed as text on a graph in the plot window. And let's just think about why I put it in the plot window. Let's go back over here and think about that. Suppose we had written the message here. Suppose we write, put an expression in here. And you say, oh, yeah, I got to put an expression in here. Before you can put that expression in here, you'd have to get that message out of here before you could type sign X. So that's a nuisance to the user to have to select and remove that message. So I put it over here, leaving this blank. So I type sign X and I hit draw, and the message goes away. So that's why I elected to put it in the plot window. Here is a more sophisticated approach to the catching errors. It's the try-catch mechanism, which is a Maple coding mechanism. It has these 4 breakpoints. You start with try, follow that with statements that might generate errors. Then you say catch. Now you can catch specific errors, or in this format, you catch any error. And then you type in here, what are you going to do if you catch an error? I don't make use of the finally statement, which things that execute whether you have an error or not. Then you end try. So let's see what that would look like here. You put try, you read the container, you draw the graph. Now, if drawing that graph generates an error, catch will catch the error. Now, notice what this allows. This allows you to catch the empty container, or the container that has garbage in it that can't be plotted. In either event, the plot command is going to generate the error, and that's what's going to get caught. And now the message is enter a correct expression. So you don't know what the user actually did. So by putting the phrase enter a correct expression, you've covered all the bases. Now let's talk about sliders. This is a slider. This is a slider. What is the difference between these two sliders? How did this slider get all these numbers on it? This is the slider property dialog. This is the slider property dialog. What's the difference? The difference is this one checkbox. Okay? Show axis labels. Okay, so you show axis labels. And what are the labels? Well, the lowest value is 0, the highest value is 100. These are the defaults, which you can change. The current position is red, that's 0. Spacing of the major tick marks 20, so it's 20, 40, 60, 80, 100. And the minor ones, these are the ones that are not labeled. If you make any of these numbers a floating point number, a decimal, 20 point, then these will all be floating point numbers. And the one more checkbox that you want to pay attention to is this one. Update continuously while dragging. Suppose you have a slider that's controlling a continuous variable. So maybe it's controlling a parameter in a graph. And you want the graph to change smoothly through these parameter values, well then you would want to click or check this box. So let's have an example of the use of sliders. So here is a plot window. Here is the slider. This is text. I've typed this in. A equals. This is text. I've typed that in. And this is a label. And so let me go back over here to this blank page and I'll show you. You would put in A equals, and then you would put in the slider. The end of the slider, you could put in an equal sign, and then you would put in a label. Right, so that's the construction here, and I'll explain how all of this is stitched together. But this is the behavior that we have created. As I move the slider, the value of A changes, and I'm graphing sine AX, and I think you can see that the graph is reflecting sine AX. And what's happening here is I'm getting a printout of the value of A, as best we can get from the pixel count here. Okay? You see, you can't get exactly 6 because of the number of pixels on the screen. Okay, so what's the coding here? The coding is behind the slider. All right, this is the coding behind the slider, and I'll explain to you what that coding is. I've made a local variable. I use capital A. I don't know why I use capital A. I could have used small a. Okay. I read the slider and assign it to A. And then I draw a graph and send that graph to the plot window, and the graph is graph of sine AX. And at the same time, I send to this label, say %label 0, a caption, parentheses caption. And the information I send to the caption is this. Now, sprintf is a Maple print, imitates C coding. I learned it. I use it. If you're a programmer, you'll be happier with it than I am. Okay, so what you put inside is this designation in double quotes, %.5, that's telling Maple 5 places after the decimal, F for float, A is the number that's being written there, and we got it. And remember, this is where I would update. I'll show you here. Nope, not there. You right click and take component properties. So you update continuously while dragging. Now, it's possible to create something very similar to that component structure through the plot builder. Okay, now if you're not familiar with the plot builder, let's just come over to this blank page. Let's put something here, sine of x. So you right click context menu comes up and you'll see plots, and you can access the plot builder. Now, what is the plot builder? The plot builder is an assistant. Okay, it's under tools, assistant. It's easy. It's easier to get at from the context menu. So plots, plot builder, and so you have this interactive structure in which you can set up this plot. So that's what I'm talking about here. Okay, so this is the first window, right? So Maple sees that you have clicked on sine AX. So it sees two variables, A and an X, and so it thinks maybe you want a 3D plot. So you have to change that. So in this window, it's a drop down, you select interactive plot with one parameter. That's what it is. It's interactive and it has one parameter. Now, at that point, Maple says, okay, this is going to be just one independent variable. And it sees it's a sine function. And it says, okay, let's default to a 2D trigonometric plot. And immediately, the bounding box x-axis goes to minus 2 pi to 2 pi because it sees a trig function. And the slider value it defaults to 0 to 10, and you can modify that. Now, if you, at that point, say, okay, plot, give this to me. This is what you're going to get. Okay? You will get this structure. Maybe we'll build this table with a graph, a plot window, and a slider, and a label. Okay, so we're getting sine of AX, the value of A is changing, and if you want this to be constrained scaling, you can do that. Or you could have used the plot builder itself. Let's just bring up the plot builder here. Plot builder. Under the options panel, you can apply options. And you see, you could apply constrained scaling before you launch the graph. Okay. All right, so you can build this same learning tool either directly from components, first principles, or you can go through an intermediary of the plot builder. Now, let's do one more thing, one more learning experience interactively. This time, we are going to build this expression. It's a sum of squares from 0 to n. We're going to have the slider control the value of n, so that as n varies, the value of that sum changes. All right, so how would you build this up? Let's give that a try. Let's go to the expression palette where you'll find the sigma. So K, use the tab key, 0, tab N, tab K squared. Now right click on that. And you see Explore. So this is giving you access to the Explore command, which we'll talk about momentarily. And this dialog comes up for the n, which is the free parameter. And here n is going to go 0 to 10. It will be discrete. If you wanted to make it continuous, you would make this a floating point number, but that would not make sense in this context. So then you click Explore, and you get this application. Okay? As n goes from 0 to 10, there you're getting the value of n, and there you're getting the value of the sum of the squares. All right, so you can build this from first principles. This is a math container. Here, right click, component properties. It's a math container, right? And a slider, and you could code this yourself directly, or you can let the Explore command do it for you. See? The Explore command has done that. There's special coding that the Explore command makes use of to build that and puts the sliders in for you. At that point, we should spend a little bit of time talking about the Explore command. Right? So let's take a look at this problem. Let's apply the Explore command to the graph of bx squared sine ay. So you have two independent variables, so you're going to get a surface, and you have two parameters, a and b. Right, and this just tells you the ranges for x and y. So this is a direct application of the explore command. You have to apply it to the appropriate plot command. So the appropriate plot command is plot 3D, because you're going to get a surface. So here's the expression. X is minus 1 to 1, y is minus pi to pi, and the view controls the height, the z height. So when you execute this command, this dialog box comes up, as I showed you before. And for A, we're going to let the values be discrete. But for B, we're going to let the values be continuous. And the decimal point will make the values of B be continuous. So this is what the application will look like. Okay, so I'm moving A. You know, if you notice here, it's discrete values of A. And here, continuous values of B. Now, what's happening at the moment is, from what you see here, the size of the image is the same because it just fills the box. But the z-axis has its scale changing because this view option hasn't taken effect because we haven't executed that command. Right? So Maple, I mean, this is a remnant from opening the worksheet. That command isn't known to this application at the moment. So what I'm going to do is go back here. I'm going to execute that command down in here, make some space. I'll execute that command here, and we'll see what happens. Okay, so I'll make this 10 point. Tell Maple to go ahead with this. All right, so let's move A and B. Now you notice the scale here stays 0 to minus 10 to 10, and you can see this, the amplitude, the surface waves changing instead of having just the scale change. Okay. Now, there's a great deal more you can do with this explore command. So this is the original version, explore this surface graph. You can state your parameters ahead of time in the explore command. A goes from 0 to 10, B goes from 0 to 10.0, and you can even tell the explore command what values to start with. Execute that command, you get this application. Okay. And you don't get the intermediary dialog box. This doesn't come up because you have assigned the parameters through the medium of the command itself. Now, what happens if you apply the explore command to this application? We define a function f of n, which is the sum of squares from 0 to n. Now, f of n is a function. We apply the explore command to that function, explore f of n, and we state that the parameters, there's only one, but this is plural, n equals 0 to 10. Now, if we move the slider now, you'll see that Maple does not know what this function is, because this is just a remnant of the execution that took place in the past. So this would need to be executed, and you can do that by clicking this single exclamation. which re-executes this command. And now Maple knows what the function actually is, so it writes f of n, and you see the value of n and the value of the sum. All right, so you can do that same kind of thing with the explore command. Here's an even more sophisticated example that you can create using the explore command. So all of these things that are showing up, right, could be built from first principles directly with components, but you can also get them via these other tools, either the plot builder or the explore command. Okay, so this example, we have a graph of a plus sine bx. What we want to do is animate on one parameter and have slider control on the other parameter. So let me just show you what it's supposed to look like. Okay, this is an animation. Let's see if that animation is live. I'll have it go on over and over again. Repeat. Okay, so there's the animation. Okay, this is I think that value is close to 0 here. All right. A is controlled by the slider, and that moves the graph up and down. Just look at the structure, a plus sine bx. Okay? I better stop that here. Hypnotic. Click here, click here. It's not going to stop. It wants to run on forever. What's going on here? Let's do that. Yes, okay, we finally got it to stop. Okay, let's examine how we did that. Okay, there is in the plots package an animate command, which will animate graphs drawn by the various plot commands. So to avoid having to put plots in front of this thing, I use the use command, as we saw earlier. Use plots in this construction and use. All right, so what are we doing here? We want to do an animation. And the syntax for this animate command is you put the plot command you want to animate. Then in a list, in square brackets, you put the arguments to the plot command. A plus sine bx. X is going from minus 2 pi to 2 pi. This view freezes the size of the viewing window. Minus 2 pi to 2 pi in x, minus 5 to 5 in y. Now this belongs to the animate command. I'm animating the parameter b, and its values run from minus 2 to 2. So that's the animation that you're seeing. The parameters belong to explore. So parameters a equals minus 3 to 3. So that allows me to raise and lower the moving wave that you see. And an initial value, start this off at a equals 10. And here's the last example of explore. This is the most sophisticated one that we've got going here. I have an initial value problem. It's a damped oscillator, driven damped oscillator. And I've got two parameters. This is the damping coefficient, and this is the stiffness. I'm going to solve this equation numerically. So this is just a model for how you would do this with a differential equation that you could not solve analytically. Because if I could solve this analytically, I'd have an expression y equals, and I could animate that, and I could do stuff with that. I want to show you how you would do this solving numerically. So here's the equation. Here are the initial conditions. This is the command for getting a numeric solution. There's the equation and the conditions. This is the unknown. Numeric tells Maple, okay, we're doing this numerically. and it takes a parameters flag option where you can declare A and B to be parameters. So before you can get something out of this structure Q, you would have to execute a statement like this: Q evaluated with parameters equal to whatever the two numbers you want to give A and B. But that would mean that you would have to do this over and over again. You would have to type this line every time you wanted to change the values of A and B. So that's tedious. So let's wrap that in a function. So y is a function that will take as its arguments the numbers that I want A to be, A and B to be. Those will go into this parameters command, and then I can apply ODE plot, which will plot the solution of the differential equation. And this is the syntax for the ODE plot command. And then I will apply explore to the function y. So in order to make this stuff work, let's make this active. Let's execute that stuff by clicking on the exclamation point. So now Maple will know what the functions are. And when I put explore on y of A and B, I can declare the parameters for A and for B. I can give initial values, and now we move the slider, and what you are getting is a graph of the solution of the initial value problem, which has been created numerically, but fast enough that there is a response to the sliders. Okay, so again, this could be built using components, but the intermediary of these tools, the explore command or the plot builder, means that the coding that you would have to do to code the components is less tedious. Now, how could you find out more information about this stuff? All right, suppose you did a search on help for a particular embedded component. Let's say you look for the help on button. Okay, you would do that by question mark embedded components, and there would be a page, and you'd have a link to button, and you would get to the button page. On that page, you would see a table like this. Option, G and S. Now this means get, this means set. This means information you can get back from that component, and this is information you can send to the component. So for example, you could get what's presently its caption, and you can send a new caption programmatically. You can enable or disable the button. You can change the size of the button. You can make the button visible or invisible. Okay, so here's a button. I believe it's button number 53. Let's just make sure that it's still button number 53. I haven't changed the document, okay? So the document tools package is where this do command lives, and I'm just going to show you what it looks like if I execute some of these options. Here I am going to send to the caption, hello. All right, so the caption now has changed to hello. Now, is this button enabled? By sending it false, that button becomes unable. See how it grays out? It's unable. To enable it, I hit true. Is it visible? If I say no, it's invisible, that button's gone. And if you don't know where that button is, and you don't know how to control it, you're dead in the water. So you want to make sure that if you make a button invisible, you know what you're doing, and you keep track of where it is and how to control it. Now you can learn a lot about embedded components by looking at some examples that are right in Maple. For example, here is a task template that I wrote. It's in Maple. Tools, task, browse. Tools, this is backwards. Tools, task, browse. I got that backwards. Never noticed that. Tools, tasks, browse. All right, that takes you to the table of contents, and these things open up. You find there's about 350 of these things. Which one is this that we're looking at today? Visualizing regions of integration. Okay. Cartesian 3D. These are the tools. It shows you a picture of what the tool is, and you insert it by clicking on one of these insert buttons. This default content means you get all the extra verbiage. Minimal content means you get enough to make it work. Okay, so I've got it embedded in here. This is a tool that will draw the region of integration for a triple integral. A triple integral, you get 6 different orders of integration. I'm going to pick the simplest one, dz dy dx. Simple integrand 1, and I'm going to go over a cube so I can very quickly, I didn't want that. Click down here. From 1 to 2 in z, from 1 to 2 for dy, and 1 to 2 in dx, just to make this thing go quickly. So this is the exact value, unit cube. And then you draw a graph, and you get a graph of the region over which you're integrating. All right, so how did this thing get built? What's here? So you can learn some stuff about this. Let's look behind the selection of the volume element. You'll see something interesting here. Edit. So this is the code behind here. Now look right up in here. Here's the module. So protect all of these variables in a module. But the module this time has a name. I gave it the name int order. You can pick whatever wacky, bizarre name you like. Some of the names I've picked is like, if I have int order, I would spell it backwards. REDRO TNI. Highly unlikely that anybody would hit that name at random. Here are locals, but there is an export, and the export is not considered a local. Okay, so here's an export. And what am I doing with this export? You see, I'm reading the drop-down list for the order of integration, but they're strings, and I don't want to have to do later on string manipulation to find out which order of integration has been picked. So I do that once over here. If this is the order, I'll use x is 1. This is the order, x is 2, so forth. So that's an export, which I can get back to later on. So let's look over here at the coding over here. So when I now want to process the integral that's been created, look at what's here. It says if x is 1, so if I have dz dy dx, then I'm going to do drawing and writing an integral in a certain way, and if it's 2, I'm going to do it a different way. But how do I access that value of x? You put the module name int order :dash x, and that goes back to the module, gets the value of x, and allows this part of the program to use that value of x. Okay, so there's a trick, a technique that you could learn from looking at built-in stuff. Here's another structure. Here I'm going to do flux through a plane curve. And you'll notice everything is grayed out, except at the beginning. So that trying to control the user's path through this complicated structure. If everything were active from the beginning, what would happen is people would click or could click on buttons at random order, and you get all kinds of error messages coming up. And I wanted to prevent that from happening at least the first time through. So let's do a very simple example. Coordinates, x, y, set the coordinates, and you notice as I do move through and do a successful operation, the next set of fields opens. So let's put y here, x here, we continue. Now we're going to do a plane curve. The coordinates of the plane curve, I set that. Now I have a place to put the parameter along the curve. Continue. Okay, so this tells me what my position vector is going to look like. I'm going to put cos of t here and sine of t here. Continue. Now I can have a place for writing the flux integral through that portion of the curve and then get the value of that flux integral. So how is this done? Well, you saw that there is the ability to make components enabled and visible or not. And that's how this was done, to coerce the user into proceeding in an orderly fashion. And then there's one other kind of example that you can learn from. Suppose you go to these math apps. Okay, so these are built-in applets. Yeah, here they are. A set of built-in applets that have been included in Maple. So let's just take any one here. Just take anything here. So this is one that was designed to help people learn about limits. If you go to Edit, Startup Code, what you will see is a complete coding of all of the components via a bunch of functions. Okay, so there's a module, and inside the module you get here's your exports and your locals and your various functions that will be called by this applet. Okay, so this is a button. Let's see what code is behind the button. You notice the only thing that appears behind the button is a call to a function that has been defined in that startup region. So this makes coding a lot simpler because you're not jumping from button to button trying to figure out who is talking to whom. You put all of that coding up front. So if you like programming, this will be very appealing to you. I've managed to escape the need to do that in the applications that I've written. And in the last minute that I'm going to be speaking here, I'm just going to point out that in this section on appendices, there's additional information. Here, I mentioned this earlier. This is getting the palettes. This talks about coding from outside the component. Now, you saw me do that already today when I explored the button. So you can write your code for the components outside the component and make the component work from this code so that you can more easily figure out what's happening, and then you can copy and paste the code when it works properly into behind the button. This talks about the older get and set property commands. The do command will do mostly what this pair of commands will do. And here I talk about the use of tables to contain on the screen these various structures.